Hey, Colin, can you help me with a question? I'm kind of uncertain about it.
What's the question?
Uncertainty.
The question or the answer?
Both.
What is uncertain?
It's uncertainty.
What's uncertain?
The question.
I can help you.
Hello and welcome to another episode of 300 Seconds of Science. My name is Sydney Carlisle. Have you ever been uncertain about something? What about being uncertain about something that you can observe and measure? Heisenberg's Uncertainty Principle covers that the position and the velocity of an object cannot be measured at the same time. Everyday experiences provide no examples of this principle. It is easy to measure both the position and the velocity of a car, for example, because the uncertainties implied by this principle are too small to be observed. The complete rule says that the product of the uncertainties is equal to or greater than a tiny physical quantity. The product of uncertainties only becomes significant for small masses of atoms and subatomic particles. The uncertainty principle was introduced by Werner Heisenberg in 1927 to develop a complete theory of quantum physics. Heisenberg had developed a quantum theory in 1926 built around the idea that only directly measurable quantities should be considered. Heisenberg had just begun his job as Niels Bohr's assistant when Schrödinger came to town to debate with Bohr. The uncertainty principle of 1927 was an elaboration of their ideas. This principle implies that the measuring instruments will not affect the behavior of the atomic objects. Evidence obtained under different experimental conditions cannot be seen within a single picture, but must be seen as complementary. Schrödinger developed a wave equation around the same time that produced the same results. The Schrödinger equation was embraced much faster. The two formulations are mathematically equivalent. Modern physicists learn both and use whichever is more convenient. Heisenberg won the 1932 Nobel Prize in Physics. Attempts to measure precisely the velocity of a subatomic particle, such as an electron, makes it move in an unpredictable way. This makes measuring these two things at the same time impossible. This result is not from the mistakes of the tools or even human error. It is caused by the connection in nature between particles and waves in the realm of subatomic dimensions. Every particle has a wave associated with it. The particle is most likely to be found in places where the rising and the falling in waves is the greatest. The more intense the rising and falling is, the harder it is to observe the wavelength. This wavelength determines the momentum of the particle. The particle, while having a definite position, has no certain velocity, because of a particle having a well-defined wavelength is longer. The particle of this wave, while having a precise velocity, has an undetermined location. The sure measurement of one leads to the unsure measurement of the other. The uncertainty principle is also expressed in a particle's momentum and position. The momentum of a particle is equal to its mass times its velocity. The product of the uncertainties in the momentum and the position of a particle equal to h/2 or more. The principle applies to other related pairs, such as energy and time. The same goes for an unstable atom or nucleus. In some atoms, the binding energy is not strong enough to keep the nucleus together, and the nuclei of these atoms are unstable. Unstable atoms will lose neutrons and protons as it tries to become stable. This is because of the uncertainty and the energy radiated, and the uncertainty in the lifetime of an unstable atom as it makes its transition to a more stable state. The uncertainty principle limits what we can know about the momentum and position of an object at the same time, yet it can improve our knowledge about the quantity we want to know at the cost of losing information about the other. In recent years, physicists have been exploring the use of weak measurements to reconstruct the average position and momentum in quantum objects. I hope you're feeling less uncertain about the uncertainty principle. It looks like this is all the time that we have on 300 Seconds of Science. Leave a comment or send us a tweet. Also, don't forget to subscribe to ZTV 300 Seconds of Science on YouTube, follow us on Twitter, and like us on Facebook. I'm Sydney Carlisle, and this was 300 Seconds of Science. So go out, enjoy life, and stay curious.
This program was produced by ZTV at the University of Akron. To find out how you can make Emmy-winning media, visit the UA School of Communication online. ZTV. Make media. Make a difference.